Lastly, a discussion of intensity. Now, intensity has to do with waves because remember, waves are a way of transmitting energy from one place to another. How quickly you transmit that energy is power, right? Energy per unit time is power. Intensity is that power per unit area. How much energy is transmitted through a given area? That gives us intensity. So you can have, for power transfer, right, you can have a lot of power going through a large area or a small amount of power going through a small area, and you would end up with the same intensity. So when you hear something, you're actually hearing the power be provided over the area of your eardrum or your inner ear. So we judge sound waves by their intensity. The intensity for sound waves is a system called the decibel system. How many decibels or decibels? So a tenth of a bell. So deci means 1/10 of, like a decimeter is 1/10 of a meter. A bell is a unit of intensity, but decibels are used in standard use for intensity. Decibel system allows how intense a sound is. A whisper versus a jet engine, right? What is the decibel range of human hearing? What are we sensitive to from an intensity perspective? What is the lowest intensity sound we can hear? And what is the highest intensity sound we can hear before we start damaging our hearing? And that's one of the reasons people who work in large manufacturing areas or airports on the runway and things like that have hearing protection. Or if you ever use power tools, you should use hearing protection because an intense sound can damage your hearing. Intensity also works with other types of waves like light. For example, the sun is producing a tremendous amount of power, right? Energy per unit time. The sun is about 3 times 10 to the 26 watts, or approximately 100 trillion watts, 300 trillion watts of power. How intense that sunlight is depends on the area that power is distributed over. For the course of our sun is in the middle of the solar system, and the power comes off as the surface of a sphere, outwards. So the total power of the sun stays the same. The sun produces the same amount of energy every second, approximately. The area depends on the area of this sphere, which depends on the radius you are from the sun. Right? The surface area of a sphere is 4 pi r squared. So as you get further from the sun, the area increases by the square of that distance, so the intensity of sunlight decreases. If you know the radius of the Earth and the sun, which you do, you can look that up in your book. If you know the power the sun gives off, which again, I just gave that to you approximately, your book would probably have a more precise number, or the internet, you can actually calculate what the intensity of sunlight is on the surface of the Earth. That intensity change is interesting because it varies with season. Now the sun doesn't, of course, vary with, the distance doesn't really change with season. The power doesn't change with season, but the intensity does because of how the sun is tipped 23 degrees on its axis. So let's look at the face of this eraser. The sunlight coming from your eyes, right, hitting this eraser, the power over this area. But now, if I tilt this eraser, the sunlight's coming in at a more oblique angle. It's spread out over a larger area. One way to think about it is take a flashlight and point it straight down. You end up with a very intense circle of light. Now, aim that beam further away from you at a more oblique angle. That intense circle of light is spread out over a larger oval-like area. So in the winter months, the reason it gets cold is the intensity of the sunlight on the Earth drops because the sunlight is coming in at more of a oblique angle because the sun is low on the horizon. In the summer, the sun is much, much higher for us in Wisconsin, right? It's much, much higher in the sky. Therefore, the sunlight is far more intense. Depositing, if it's more intense, more power is deposited per unit area. which means that the ground is warmed up. We end up with hotter days. It also explains why NASA cannot use solar-powered spacecraft to venture into deep space. The area that the sunlight is spread over goes as the square of the distance from the sun. So twice as far from the sun, you get 1/4 the sun's light, the intensity. 3 times far from the sun, it drops by 1/9. 4 times as far from the sun, it drops by 1/16. By the time you hit Jupiter, in our solar system, the sun intensity is so low, you can't really use solar power to power spacecraft anymore. And that's why deep probes like that tend to use nuclear power. So this is intensity, which is a measurement of power of a wave per unit area.